So this lesson will cover material from Chapter 3, and Chapter 3 is on logic. So logic then consists of statement, and so a statement is a declarative sentence that is either true or false. So it's going to either be a true statement or a false statement, but not both. True and false. Right? So a statement that only has one truth value, either it's a true statement or it's a false statement. So for example, if I have something like this, Mount Rainier is a national park. That is a statement. It is a true statement. So that would be an example of a statement in logic. Now, in terms of statements, then we have what it's called a simple statement. So a simple statement conveys only one idea. And then a compound statement conveys two or more ideas. Right? So simple statement and compound statement. Right? Right. Well, in terms of statements and statement types, we can have, so build a little table here. So we're going to have in terms of the statement, and then we'll have in terms of its connective, and then the symbolic form for it, and then what kind of type is it, right? So first off, we have not P. So the connective here is not. The symbol is going to be this. And this type is called a negation. Okay. Okay. The next one is going to be P and Q. And so here the connective is and. The symbol is going to be this. And this one is called a conjunction. The next type is P or Q. And here connective is or. And the symbol here is that. And this one is called a disjunction. Okay. And then we have if P, then Q. And so this is an if-then statement. And the symbol here is this arrow. And this is called a conditional. And then we have P, if and only if Q. And so this type is called an if and only if statement. Okay. And the symbol here is this double arrow, headed arrow. And this one is called a biconditional. So we have in terms of different types of statements and what they are. Right? Well, in terms of statements, we can talk about the truth value. So the truth value of a simple statement is true or false. So it's either true or it's false. So either true, which will show by capital T, or false, which will be capital F. So it'll be either true or false. Like my statement I had up earlier, Mount Rainier is a national park. It's a simple statement. And the truth value of that is indeed true. Right? And then the truth value of a compound statement So compound statement, a bit more to it, depends on the truth value of its simple statements, and its connectives. And we'll see how all this comes to play a bit later when we talk about truth tables. Right? Right. So truth tables and truth values of statements. Right? So a truth table shows the truth value for all possible combinations. So let's look at a simple couple of statements and how this works. So for example, if I say that today is Tuesday, and then I will put out the garbage. So let's make a simple statement. And so if I say, okay, if today is Tuesday, then I will put out the garbage. Right. So simple. So we have our statement. Right? And so I could write this in terms, basically then this is an if P, then Q. Right? So if I said then that this is the P and this is the Q. Right? So if today is Tuesday, then I will put out the garbage, and that it would be true because that is the day of the garbage pickup around here where I live. Right? If I write this then, if today is not Tuesday, then I will not put out the garbage. Right? And it's garbage, sorry. And if I represent that, then this would be not P, then not Q. Okay. Okay. So in terms of these things that connect my P and Q, and in terms of their truth values, we'll go through some of these. So the first one then is the truth value of a conjunction. So a conjunction basically then in terms of everyday words, this is an and statement. Right? So if I have P and I have Q, and I want to know all the possible combinations of P and Q, then this is going to be T, T, F, F, T, F, T, F. And the way you get the number of possible combinations, again, there are two possible outcomes, either true or false. And so the way you get the number of possible outcomes is going to be 2 to the n, and n is the number of items or statements. Okay. So now I know what's the truth value here of a P and Q statement. Right? So a P and Q statement then. So true and true is true. Okay? So an and statement is only going to be true if both parts are true. Okay? So an and statement is only true if both pieces of that statement are true. Okay? Only time that will be true. Okay? So then the next type, and so actually I'll put that down here before we go on. And so and statement is only true when both parts are true. Okay. Then it will be a true statement. So that's my and statement. Okay. So then the next one then is the truth value of a disjunction. Okay. And then in terms of everyday words, this is going to be the or statement. And again, if I do P and Q, again, the possible combinations, and we get this, so we have this again, and now we want P or Q, and so an or statement will be true as long as one part of it is true. So here we get T, 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 and then this is false. So an or statement is true as long as at least one part is true. Okay. So as long as one part of that statement is true, then the whole statement is going to be true. Mm-hmm. Right. Well, in terms of my ands and or statements, we get into some of the various laws. And so here we have, in terms of De Morgan's laws for statements. Right. And so here we got two possibilities. So not P or Q is equivalent to not P and not Q, and then the other one is not P and Q is equivalent to not P or not Q. So those are equivalent to each other. And so the way we prove that things are equivalent to each other is by seeing if the truth tables come out to be the same. So let's look in terms of that first one and prove that they do give me the same truth tables. Okay. So let's do this table. So we have P, we have Q. And again, the combinations T, F, F, T, F, T, F. And then we're going to have P or Q. So breaking this up into pieces here. Okay. And so again, this is an OR statement. So again, we said that's true as long as at least one part of it is true. And so we get that. And then lastly, we want the negation of that. And so we would end up with F, 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 and T. Right? So that's the left side of that first one. So now let's do the other side and see if this comes out to be the same thing. So now we have P and we have Q. So again, T, T, F, F, and then T, F, T, F, right? Right? And now we want to have not P for my next column. And so that's going to be F, F, T, T, and then we're going to have not Q for the next one. So F, T, F, T, and then lastly, we will have not P and not Q. Okay. So false and false is false. False and true is false. True and false is false. And then true and true is true. And so if I look at this, I notice that this column here and this column here are exactly the same. And so they are equivalent. Right? So that's how you prove statements are equivalent. They should give you the same value in terms of the truth table. Right? So in terms of if-then statements, and how does that work for them? So let's do this. So we want if P, then Q. So let's say here then for an example that P is going to be, I get a 70 or better on all assignments. Okay. So you think about in this class that you're taking, you get a 70 or better on all assignments, and let's say then Q is going to be, I will pass the class, right? Right? And so my statement then is going to if P, then Q. So if I get a 70 or better on all assignments, then I will pass the class. Now, what about the truth values for this statement? So let's make a table. We got P, we have Q. So T, T, F, F, and then T, F, T, F. And then lastly, if P, then Q. So the first possibility, true and true. Yes, you get a 70 or better on all of the assignments, and you pass the class. True. Okay. Second possibility, you get a 70 better on all the classes, but now we say you do not pass the class. Well, that's not going to happen. So that's not, so that's going to be false, right? So if you got a 70 better on the class and I end up giving you a failing grade in the class, you will most likely complain right away and make sure I get your grade changed, right? So that's next possibility. You don't get a 70 or better on all assignments, but you still pass the class. Well, that is a possibility, right? You can still pass the class and not get a 70 or better on everything. And then lastly, you don't get a 70 or better on everything, and you do not pass the class. Well, that is possibly true, right? So we have, in terms of our truth table, for our if P, then Q. Right? And that in terms of if, then P, then Q statements, we again have in terms of equivalent statements. Right? And we won't prove one of these, but if you want, you can always do that. And so if P, then Q is equivalent to not P or Q. And that in terms of the negation of this, we have, oh, sorry, let's try this again. There we go. There we go. Negation. Right. So not P, then Q is equivalent to P and not Q. And then the other kind of statement then of the group is a thing called a biconditional. And so this is your if and only if. And the way you'll see this sometimes abbreviated is IFF. And so now we have P if and only if Q. And the truth values for this statement, and T, T, F, F, T, F, T, F. And so we get P if and only if Q. And so this one is true if both parts are true or both parts are false. So we have the truth values for our and, the or, the if then, and then the biconditional if and only if. Well, in terms of our if then statement we had if P, then Q. We have several types of statement. The first one is the converse. And so the converse is going to be Q, then P. We have the inverse, which is going to be not P, then not Q. And then we have the contrapositive, which is going to be not Q, therefore not P. All right. So now we want to look in terms of those things called truth tables. But before we do that, let's pull up again our tables we made earlier. So let's get those up here. Right? So let's just pull those in. Right? All right. And then let's do this one. Okay. I guess get them all up here again. And paste. And then this one. Right? So we have our various truth tables, the and, the or, the if then, and if and only if, right? So we'll pull those, make those handy because we want to look at constructing a truth table for a given statement. And so let's pull up this one now. Okay. And so we're going to have this one here. Okay. All right. And going to do it. There we go. We got it. All right. All right. Make this a bit bigger, easier to see here. Open this up a bit. All right. All right. So we want to construct this truth table that is going to be for this statement. If P, then Q, and R, if and only if, not Q, or not R, right? So we want to construct the truth table for that. And so that is what this table here is. So you notice that in this case, I have a P, a Q, and an R. So I have a P, I have a Q, and I have an R. Okay. So now I have 3 items in this one. So that means I'm going to have 2 to the 3rd, and that is going to give me 8. So you notice here that I have 8 boxes. So I got to have, so now the way we set this up then, make sure we get all the possibilities. So here we're going to have T, 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 and then the next 4 are going to be F's. Okay. And then the next one, here we go T, T, F, F, T, T, F, F, right? So that's my Q's. And then my R's, we're going to alternate T, F, T, F, T, F, T, and F. Right? So we got the P, the Q, and the R. And again, so that's our pattern. So we go 1, 1, and then we go 2, 2, and then we have 4 and 4. Right? Right? So the truth tables can get rather big and messy as the number of items go up. Because after all, if I had a P, a Q, a R, and an S, then at that point I would be up to 2 to the 4th, and I would end up having to have 16 rows to do the truth table for this. All right. So we got our P, our Q, our R, and so now let's start working out what this is going to be. So the next one I have here is I want not Q. Well, that just means I'm going to just do the negation. So this is going to be false, false, true, true, false, false, true, true. Okay. And then we're going to do not R. And so we get F, T, F, T, F, T, F, T. Right. Right. The next one I have here in my table is to do the if P, then Q. Right. And so we have if P, then Q. We have it over here. Right. and I want to know the truth value for this. So we have T and T is T. T is true. T and F is false. T and F is false. And then false and true is true. False and true is true. False and false is true. And false and false is true. Okay, the next part is the if P then Q and R is the next part. So again, my AND statement is only true if both are true. So true and true is true. True and false is false. False and true is false. False and false is false. True and true is true. True and false is false. True and true is true. And then true and false is false. Right. And so we have that one. Right. The next part then is not Q or not R. And so we would have here false. Okay. And the next one is true or false, and that is true. False or true, that is true. True or true, that is true. False or false, that is false. True or false is true. False or true is true. Or true or false is false is true. And then true and true is true. Okay. And then lastly, we get to the entire statement at the end. And that was that if P then Q and R, if and only if, not Q or not R, right? So now we're down to our if and only if, and if and only if is true only if both parts are true or both parts are false. And so now let's do this final one in a different color. So T, if and F, so T and F, this is going to be false. FT is false. FT false. FT false. TF false. FT false. T and T, that's true. And FT, that is false. Right? So we see in the case of this one, it only comes out true in only one case. Right? So only true, it's only true on this one line of stuff. Okay? This is the only time the statement is true. So it only happens once here. Okay. So it depends on what the given conditions were, whether or not this will be true or not. Right? Well, there is ones like that where depending on what you were given, whether or not it's going to be true or not. But then you get if other kind of statements, which are these, and that is if it is always true. So always true. Then it is called a tautology. Right? So if I build my truth table and I get to the far end and I get that no matter what, it's going to be a true statement, then that is called a tautology. And then, of course, you could have the opposite of that, and that is if it is always false, then it is called a contradiction. Okay? Okay. And you get that part. So it could be a contradiction. If it's always false, it's a contradiction. Okay? Yeah. So we got given our and, our or, our if then, if and only if. We can talk about the truth values for those. We can also talk about when we put together compound statements and come up with a truth table and prove if it is true or not. And if so, under what conditions? If it's always true, it's a tautology. If it's always false, it is a contradiction. Well, then you get in terms of arguments. And so here in logic, you get that an argument consists of a set of statements. And these statements are called premises. And another statement called a conclusion. So an argument consists of an opening set of statements, which are called the premise, and then the last statement is called the conclusion. Okay? And then an argument is valid so an argument is valid if the conclusion is true whenever all the premises are assumed to be true. Right? To be true. Right? All right. So in terms of an argument, let's look at a simple example of this. And so we have our first premise is this. And this one comes out of the book. And that is if Aristotle was human, then Aristotle was mortal. Right? Second premise. Right? Second premise. Aristotle was human. And so then, therefore, our conclusion is that, therefore, Aristotle was mortal. Right? Right? So if Aristotle was human, then Aristotle was mortal. Second premise, Aristotle was human, therefore Aristotle was mortal. And so yeah, both premises are true, and they're in their conclusion true. And instead of the therefore, the way you'll see a lot of this in terms of arguments is the therefore, we will substitute in this 3 dots. Those 3 dots stand for therefore. So if, on the other hand, if the conclusion is false, given the premises were true, then the argument is invalid. So in terms of arguments then, there are some standard forms for valid arguments, and so there's 4 of them that are given in your book. So let's just go over those quickly. So standard form for 4 valid arguments. Okay. So the first one is they call in the book direct reasoning. So if P then Q, if P then Q, and second premise is pre, and then the conclusion is Q. Right? And again, if you go back to your if-then statement, again, we're assuming that if P then Q, again, the whole thing here is you assume that this is true, okay? So you assume the if P then Q is true, right? So if that's true, P is true, okay? And so if P is true, therefore Q had to be true, okay? And you can verify that, again, by looking at that table for if P, then Q. The next type then is they call contrapositive reasoning. And so now we got if P, then Q, not Q, and so therefore not P. Right? The next type then is transitive reasoning. And so now you have if P, then Q, if Q, then R, therefore, if P, then R. And you may remember seeing something like this in terms of maybe some of your other math classes. You may have seen something that said, like, if A is equal to B and B is equal to C, then A had to equal C, right? And then the other type then is this. It has to do with disjunctive reasoning. Okay, and so now you get 2 cases here. So you got P or Q, not P, therefore Q. And then we could have in terms of P and Q, right? Not Q, therefore P, right? And actually, let me just check something here on that one. All right. So we have in terms of our statements and in terms of arguments, and what makes it an argument valid or not. Yep, sorry. Yep, didn't make a mistake there. Thought that was true. This should be this way. All right, there we go. Got that right. All right. Okay. So we have in terms of types of arguments and the valid forms of those types, right? Right. So let's look at an example and decide if it is valid or not. Right? So let's say I have something like this. So the question then is this argument valid? Right. So if I attend all my classes, then I will pass all my classes. Right? So that's my first premise. Right? Second one is I did not pass all my classes. Right? And so therefore, I did not attend all my classes. Right? Right? So we want to see, is this a valid form or not? So let's look and see what we have here. We have that this is going to be in the form of, right? There's going to be if P, then Q. Right? I did not pass all my classes, so this is going to be not P. Or not, I did not pass all my, sorry, that's not going to be, sorry. That's actually going to be not Q. Did not pass all my classes, so that's not Q. And so then the conclusion, therefore, was not P. So now the question is does this match up with any of our forms? Right? And so let's go back up and let's take a look and see in terms of our forms. And do we have one that looks like that? We have, yes we do. We have that one called the contrapositive reasoning. It is an argument that is in that form. Okay? So yes, this is a valid argument. Okay? Right? And again, this is in terms of contrapositive reasoning for this one. Right? So it is in a valid form. Right? And then the chapter does finish off with in terms of argument and deciding, you have what are called Euler diagrams. So I can make a diagram to show what's going on. So if I do a diagram like this, no cats are dogs. And so I can make a diagram that shows that. Right? So we gotta have, this is going to be, let's say that this is my cats. And then we can say, okay, this is going to be dogs. So that would be a diagram that shows that no cats are dogs. After all, they are separate, they are distinct, they do not overlap, okay, in terms of this. Okay? Okay. We could have one that looks like this. All cats are mammals. And if I had the diagram for this one, right, and so we could say my big circle here is going to be mammals, and then my inner circle is going to be cats. Okay. Right. And so we could have, and so my inner circle here, this is cats, right? Okay. And then we could talk about whatever a particular cat. So we just put a dot in to represent our cat. Okay. And we could do the same thing over here. Let's do that. We could put in a dot. Let's say that this is some cat, whatever that may be. Okay. A couple other possibilities then in terms of these diagrams. And so now we could have one for this one. And that is that some dogs are pets. So we could have a circle. Let's say this represents, so this is going to be dogs, and then we have another circle, and this is going to be pets, and then we have our dog, our thing we're talking about, and so some dogs are pets. Okay. And then we could have, and the next possibility is that some dogs are not pets. Okay. And so again, if I make a diagram again of this, and so again, I can have my one circle. So let's say that this is dogs. We have my other circle. We'll say that this is going to be pets. And then we can say, okay, so here is my dog. That's a dog, but it is not a pet. The other thing the book does mention, and I'll just put it in here, and that are what are called quantifiers. And those quantifiers are either some, and the other one is all, right? Now we just saw those earlier. I said some dogs are pets, and then all cats are mammals. So those are quantifiers in terms of what they are. Those are called. And that will conclude this segment, right?